All right, let's get started with the next session. So first we have Schuyler and Adam with Annotations and Hardware Construction Languages.
So hi, my name is Schuyler Eldridge, and I'm presenting some work today on behalf of some of the main FIRRTL developers. I'm going to switch off to Adam halfway through. But what this is about a concept which you may have heard of kind of in passing, but it's trying to sort of flesh out what that is. And this is about annotations and how they relate to hardware construction languages, specifically in the Chisel and FIRRTL hardware compiler framework. Okay, so big high-level concept. If you get nothing else out of this talk, remember two things. So annotations are about metadata and specificity. Specifically, annotations are metadata, and there's a lot of problems that come up, which Adam has figured out, about how you attach them to specific things in a circuit. And if that's all that you get, then that'll be great, and you'll remember that if you want to write some complicated front-end, back-end, or if you want to write FIRRTL compiler passes to do something efficient, then refer back and dig into some of this talk or some of the other material about annotations. But to explain this a little better, I first need to sort of provide my own view of how I like to talk about Chisel and FIRRTL, or this, as Adam and then Krista and Bora have picked up, Chisel and FIRRTL hardware compiler framework. And what this is that you start with something high level, some Scala program that describes a circuit. That runs through the Chisel front end. That emits FIRRTL IR. So this is circuit IR. It's like LLVM IR, but it's circuit IR. That runs through the FIRRTL compiler, optimizes. It's an optimizing compiler. That then outputs some low FIRRTL, and then that's converted to Verilog. Now, obviously, you could extend this going up, like with spatial. You could extend it going down, like with some work that Edward Wang has done related to Hammer. But the other thing here is that there's really two things that are being emitted by each one of these stages in the compiler. You have a circuit, and you also have some annotations. So instead of like diving in on everything that an annotation could be, it may be easier to then explain this with a small example. So this has been mentioned, I think, by Richard earlier, but there was a recently added Chisel API called Boringutils. And interestingly, this actually fills out a concept in a paper published by Michael Plower and Joel Emmer on soft connections. So basically what it means is that I would like to be able to connect two things in a circuit, but I don't want to do them at chisel time. I want to do them later. So basically, effectively what it is if you don't have a tunnel boring machine, you can use Boringutils to then bore through your circuit. So on the left, what this is showing is that I use the Boringutils object with the bore method, and I want to connect my instance foo.x to bar.y. And if you then look at the top, nothing's connected initially, but this is because we're still at the Chisel, the FIRRTL emitted by Chisel. But additionally, there's a bunch of annotations, and annotations really are JSON. And in this case, it's something talking about a source annotation, a sync annotation, but I'll get into more of what that is on the next slide. So switching gears from Chisel time to FIRRTL time, at FIRRTL, these annotations are picked up by a transform called the wiring transform. And what this says is it says I look through my circuit and I see, hey, the user told me that I should wire up top.foo.x, that's my source, and I'd like to connect that to top.bar.y. And it says, okay, fantastic. I go and I look at the circuit and I figure out what's the least common ancestor between these two components. Well, that's top. I'm then going to drill up from foo into top and then down into bar. Okay. So there's also some additional annotations here related to don't touch. All this is saying is just that foo.x is not driving anything. Don't delete it. I really do need it. And there's also some stuff related to deduplication, but just ignore that for the time being. But basically, this is showing what you can do with annotations. So basically what this is this is metadata associated with foo.x and bar.y. However, it's much more than that. And that's kind of what I was getting into on this slide, is saying that these are arbitrary metadata. It's literally whatever, it's a container for whatever information you want to put into it. And you can really extrapolate that far when you think about a hardware compiler framework, right? So on the Chisel level, you have things like Boringutils, inline/flatten instances, as well as load memory from file for doing things like boring through a circuit, inlining or flattening instances, or hooking up and initializing Verilog memories when you run your Verilator simulation. However, you can also effectively use these to control things that are happening in the hardware compiler framework. So things like the target directory annotation for controlling what build directory you're using, what the compiler name annotation is, what compiler I want to run, what circuit I want to omit, or even really a FIRRTL circuit annotation for encapsulating an entire circuit. Well, wait, I started this whole thing talking about you have a circuit path and you have an annotation path, but the annotation path can effectively subsume the circuit path. So really what that comes up with is this concept that we've been floating around with this RFC here, FIRRTL 764, of everything in this is a stage. And really what that means is a stage is a mathematical transformation on a sequence of annotations. And a sketch of what that API looks like here, but you can kind of ignore everything, but just look at the middle method. In that what a stage is doing is it's taking some annotations and transforming those annotations. And the key thing here is that then if you want to go and write your own front end or your own back end, all that you have to do is align with this API which we're trying to present. And it all hinges on this concept of annotations and annotations containing certain metadata and doing things with that. So however related to the problem of specifying specific things in the circuit, I'm going to hand off to Adam, and he's going to continue the talk.
Great, thanks, Schuyler. So now we understand we have metadata. It can be really arbitrary stuff that you can put in, and we'll get passed all the way through the compiler. But what if I want to attach this, or I guess point this information to things in my FIRRTL circuit? So sort of the other question is like, what types of things can I annotate? So annotations can refer by name to any FIRRTL thing. So we call this a target, and you're going to see, I'm going to talk about more about this in the next slide. But it's important to, as sort of Schuyler said, annotations are not kept in the circuit AST, and because of that, they can have 0 targets, 1 target, many targets, etc. So you can have these multi-target annotations that hold all the metadata you want, and that actually turns out to be very powerful. The other thing that we do is every annotation has an update method, which is called after every FIRRTL transformation. So what this does is it specifies how this annotation should modify itself given changes to the FIRRTL AST. Okay, so what does that mean? I'll go into more example. Actually, we have the Boringutils annotation update method at the bottom. So suppose I call this update method and I said, oh, the target that you're annotating got renamed. The annotation can decide what its behavior should be. If you're not supposed to rename me, I can error. And that's actually a really good thing because you can specify exactly what your behavior is. Or you could say, oh, renaming me is fine, so I'm going to just propagate myself, annotate the new thing. Okay? If you don't want to worry about this, that's fine. We have lots of default implementations for different types of annotations. So back to this target concept. So this refers to a FIRRTL thing with a name. And here's just a table of lots of different things you could annotate. Okay? And it has its own sort of special syntax, but on the right is the description. So you can annotate, you can target the circuit, you can target a module in the circuit, you can target a reference in a module in a circuit, and you can even target a reference in an instance in a module in a circuit, or a reference in an instance in an instance in an instance of a module in a circuit. Okay? And that's another advantage you get by not keeping the annotations in the actual AST. You can actually refer to things that don't fully exist in the AST, and you can let some downstream transform handle it. The other thing that we've added is this automatic renaming. So if some transformation does lots of changes, we can record all of those and then calculate, if you have some target, what the new target should be under these different types of renames. So in this example, if we rename module food to module cux, then, and that's represented by that AST change column, we can automatically rename all of these different types of targets. So if you were targeting the module foo, it can correctly be renamed. If you were targeting a reference inside of foo, that'll automatically be renamed to a reference inside of cux, and so forth. Okay, all of this is done for you. So you get this very robust annotation I guess, API and mechanism to preserve your information and what it targets throughout sort of arbitrary transformations to your FIRRTL circuit. Why spend all this time doing this? Why do you guys care? Well, hopefully you won't have to care because it'll all just work. But the biggest reason is we want to enable composability of arbitrary transforms and arbitrary annotations with each other. So that you get this problem, but if you're combining arbitrary behavior, what's the defined behavior of the combined of them? And often things can't combine. They have undefined semantics. And in those cases, you want to be sure that you can err for the user and not just silently delete annotations or emit bad code or whatever. You want users to be able to just download some transform from the internet, plug it in, and if it works, it works. If it doesn't work, then I need to think a little more. Okay? So, in other words, what happens when an unstoppable force meets an immovable object? Err nicely to the user. That's the goal. So the big takeaways are that annotations are just containers of information. They're kept to the side of the circuit. And we have this concept of a target, which refers to named FIRRTL components. These annotations can just reference, because they contain information, they can contain targets, and they implement an update method. And a library writer can decide exactly how their transform and the corresponding annotations to that transform should interoperate with changes to their targets. Okay? So that's all. I guess we got some extra time for questions. So thank you all so much.
Any questions?
Can you give an example of how annotations are used in like an existing FIRRTL transform? Just maybe to...
Yeah, so like a good example is the don't touch annotation. So often you don't want, if you're trying to debug something and you have some unconnected wire, it'll get constant propped away or dead code eliminated or something will happen to it, some optimizing pass. So we've exposed a don't touch annotation which targets one named thing, and those optimizing passes will ignore that field. Yeah, so that's one example. But we have stuff like build information is another annotation that doesn't actually target anything in the circuit, but will still get propagated through. So that is to like generalize this annotation concept.
Just a question on the connection. Do you have to connect given the entire path, or can you say instance connects to instance, and it'll find those two instances and connect them?
Yeah, so in the specific...
Like the bind, like a system Verilog bind.
Yeah, well that's for the Boringutils, but yeah, you don't have to provide the full path. It sort of tries to figure out if you instantiate the module multiple times, it'll sort of assume, it'll try and assume it knows what you're doing. You don't have to use the path, but I think Schuyler has more thoughts.
Yeah. So currently, the current version of the wiring transform sort of predates a lot of the target work that that Adam did, and part of the problem there is that you could only really annotate things which are like a module, and the problem is then you have to then go and try and figure out what the user meant. So a good example is like if you have an 8-core rocket ship and you want to then go and wire from something in like the cache over to the data path or something like that, you then kind of have to go and figure out what the user meant, because the annotations at the time were not sufficient to describe what you really want, which is, I want to wire every copy of this instance to this instance. So the thing is now a lot of that's solved, but the way the wiring transform did that before was that it would try and figure out what the user meant, which is basically you could only wire one source to multiple sinks, and you would then define a distance metric, and based on that distance metric, wire to the closest things. So for most cases, it would do what you want, which is, I have a bunch of copies of an instances, I want to wire within those. If you wanted more complicated semantics, like if I wanted one rocket ship cache to be wired to all of the other ones, all of the other data paths, that would be more complicated. But a future refactor will help enable that based on a lot of the work that Adam did with Target.
Another question?
In my current setup of verification, I use a black boxing technique for keeping signals alive. So now, can I use annotations instead for that? And if I can, then which will be a preferred way to do that?
I missed the last part of the question.
So can I use annotations for keeping signals alive? Like in my formal verification setup, I need to use non-determinism. I need to keep signals alive so that it's not optimized away. But today
Right.
I do that by using black boxing technique.
Okay. So you should be able to use the don't touch annotation, which should keep them from being optimized away. I don't know if that's your question.
I did
but-
try don't touch once, but
it didn't work?
probably did not try enough, but it did not
Okay.
work in the first place.
Then that's probably a bug. So it should work. But if, yeah, I think that is the answer to your question.
All right, I think let's thank
Okay,
the speakers. And next up, we have Steve Burns talking about a fertile pass for area and timing.